All right, folks, let's get started. So we've got an exam coming up on Monday, and as much as I'd love to barrel through and do more Chapter 10 stuff, I should probably take a moment and at least address review stuff to make sure you guys are on the same page when it comes to this upcoming exam. So the exam on Monday is going to cover chapters 7, 8, and 9, but not 10. And that means that you've got to understand the big concepts for those three chapters. The crux of chapter 7 was the introduction of the concept of energy and energy conservation. Oh, camera's all wacky. There we go. So in order to do stuff in chapter 7, you had to first know how to compute the amount of work done by a force. How do you calculate the work done by a force? The definition of work was the dot product of the force exerted on an object times the distance through which that object moves, right? If you push an object but it doesn't move, doesn't matter how hard you're pushing, if it doesn't move a distance, it's not doing any work. Now, this is the first time we'd ever seen a dot product in this class. Dot product happens when you multiply two vectors together, but your answer is a non-vector. And the way we dealt with that was that we took the magnitude of f, which is just a number, and by definition is always positive, times the magnitude of the distance. But then to deal with the direction, we would multiply by the cosine of the angle between the force and the distance.
This is chapter 7.
And that was work. Work is, of course, measured in units. The unit of work is going to be a Newton times a meter, which we call a joule. Amber, what's up?
This is chapter 7, right?
I can't hear you, Amber, if you're saying stuff. Hang on, do I have my volume down, maybe? Did you have a question, Amber? Okay, I guess not. All right, I will move on. Yes, this is chapter 7, Amber. Yes. All right. So that was the first major concept in chapter 7, this idea of being able to calculate the amount of work being done by a force. Certainly you should be able to do that on the exam. It may be part of a problem. The reason we introduce the concept of work is because energy is the ability to do work. So every time you do work on an object, you can think of that as giving the object energy. And when you do negative work on an object, you can think of that as taking energy away from the object. So work is a transfer of energy, and that's going to be important. We next learned that there was a relationship between the amount of work done to an object and the kinetic energy of an object. Kinetic energy, of course, is the energy something has invested in its motion, and it was defined as 1/2 mv squared. That is the kinetic energy of an object. And kinetic energy was related to work because according to the work energy theorem, if you looked at the net work being done by all the forces that are acting on an object, that net work will add up to the amount by which that object's kinetic energy has changed. So if you do positive work on an object, that should cause its kinetic energy to go up. It should go faster. If you do negative work on an object, that should cause the object to slow down because you'll be reducing its kinetic energy. Now, we took these concepts and applied them specifically to forces in which are situations in which all the forces acting on an object were conservative. So you should certainly know the distinction between a conservative and a non-conservative force. Conservative forces are forces for which you can make the following statement: that the total work done by that force over any closed path, by which I mean you start someplace and you end up eventually returning to where you began, conservative forces will do zero work over that path. All right. So if you have a force which is a conservative force, you know that it's going to do work in a really predictable way. And that's going to allow us to solve lots of problems because we can determine how much the kinetic energy in an object has changed without needing to worry about what path an object took. Because if it always has to do zero work over a closed path, that means that if you go from point A to point B, well, no matter how you get back to point A, the work's going to always have to be exactly the same as it was going from A to B. So for conservative forces, the work won't depend on the path you take. Now, examples of conservative forces: gravity was a conservative force. The force of a spring pulling on something, or a rubber band stretching, those are conservative forces. Forces that are non-conservative would be things like friction or air resistance. If I move forward, air resistance pulls me backwards, causing negative work to be done. But when I turn around and reverse direction to go back to where I started, the force of air resistance also reverses. So it does negative work both on the way out and on the way back, and therefore does not add up to zero. So you should definitely know the distinction between conservative and non-conservative forces. Now, the bulk of Chapter 7 involved us solving energy conservation problems. Energy conservation problems exploit the behavior of conservative forces and the work energy theorem and allow us to make the statement that if there are no non-conservative forces, the total mechanical energy, kinetic energy plus potential energy, has to be conserved. A spring is a conservative force. That's correct. And in fact, any force that is conservative will have a potential energy formula. So if we learned two potential energy formulas this semester, one for gravity and one for springs. And so the fact that those formulas exist tell me that it's a conservative force. So potential
Dr.
energy.
Fleming, is that supposed to be an F, U, KF plus UF? Or?
Yes. Okay. Good catch. So, that's certainly true if all the forces are conservative. And of course, you know that U has several forms depending on what kind of forces you're talking about. For gravity, U is equal to mgh. For a spring, U is equal to 1/2 kx squared, where k is the spring constant of your spring, and x is how far your spring has been compressed or stretched. And you can use this expression anytime you know there are no non-conservative forces. But even if there were non-conservative forces, you can still sort of use this. You just have to tweak it a little bit. Because this says that if there's no non-conservative forces, the energy I start with is the same as the energy I finish with. If there were non-conservative forces, those non-conservative forces may end up transferring me extra energy, or they may be taking energy away from me. So my starting energy and my ending energy might be slightly different. But the amount by which they will be different will be however much work those non-conservative forces did. So all I have to do in the presence of non-conservative forces is add a term. So I can just simply add in the work that those non-conservative forces did, and I'm good to go. So those are the big concepts that we doled out in chapter 7, most of your problems are going to involve, some use of this energy conservation relationship, and it's going to be incumbent upon you to be able to think through them. So, any questions about the big ideas back in chapter 7? Allergies. I'm allergic to the state of North Carolina. This kills me. All right. Let's talk about chapter 8 for a second. So chapter 8, much like chapter 7, centered around a conservation law. A conservation law says that there's some quantity that no matter what you do remains unchanged. But the concept of conservation in chapter 8 was the concept of momentum conservation. So, of course, what is momentum? Momentum is the product of mass and velocity. Notice that velocity is a vector, which means that p is also a vector. And you can think of momentum kind of conceptually as a measure of how hard it is to make something stop, right? If you've got a large mass, it's difficult to make you stop. If you're traveling really fast, it's difficult to make you stop. If you have both a large mass and you're traveling really fast, it's crazy hard to make you stop. That's what momentum is. And because of Newton's third law, it turns out that if you have a system of particles, in other words, multiple objects, and those objects are in a closed system, by which I mean that they're interacting with each other, but the objects aren't interacting with anybody else besides the ones in my little group of particles. If that's the case, I have a closed system, and what that tells me is that if I add up all the momentum of all my particles before the collision, well, that's got to be the same as the momentum of all my particles after the collision. So this is the statement of momentum conservation. And all you've got to do to solve a momentum problem is figure out what the sum of the momentums is before, add them up, figure out what the sum of momentums is after, add them up. That's going to give you one or more equations, and then you'll solve them. Super easy. One little aside that you probably have to wrap your head around. Sometimes sorry. Let's write it the other way. So this is called the impulse momentum theorem. You'll notice this makes a direct relationship between how much momentum changes and how hard you're being pushed, or how much momentum changes and how long you're being pushed. For a take-home exam, you probably should be at least familiar with that. It may show up. What's the implication of this? Well, it explains stuff like why seatbelts prevent you from dying in a car crash, right? If you are in a car wreck, your momentum is going to change. You're going to go from having lots of momentum to being stopped. But if you're wearing a seatbelt, what's going to happen is the minute your car starts to stop, the seatbelt starts to stop you as well. So you're slowing down for a longer portion of the crash. Because the time of which you're slowing down is longer, it means that the amount of force you have to have exerted on you is much, much smaller. If you're not wearing your seatbelt, then what happens is your car starts to stop, but you don't. You keep going forward for a while. And you're going to go forward until you hit the dashboard or the windshield or the steering wheel or whatever. And that means that you're not stopping for the same amount of time that the car is stopping for. You don't start to slow down for a split second until after the car is already stopped, which means in order for you to stop, the force exerted on your face by the steering wheel or the windshield or whatever must be considerably larger. Sometimes, several factors of 10 larger. And that's why seatbelts are good. Wear your seatbelts, kids. Public service message. So when you solve momentum problems, we had them in a couple broad varieties. The first of them were what we call 1D collisions, because momentum conservation problems almost always are in the form of two objects colliding with each other. Now, what do I mean by 1D? It means that all the motion was along a single direction. So if I had, say, two objects and they were both moving in one dimension, the P initial is just going to be the momentum of object one before they collide, plus the momentum of object two before they collide. And afterward, they might have different momenta. But in one dimension, all the motion is along a straight line, so all I have to do is literally like write one equation. Now, if I had a two-dimensional collision, well, what's going to happen is P, being a vector, is going to have components. And when you add vectors, you add them component-wise. In other words, the x component of one vector adds to the x component of the other vector, and the y components add to the y components. So in a two-dimensional problem where things are moving diagonally or in more than one direction at once, what you'll have to do is just additional collisions. You'll have, something like, M1 V1 initial in the x direction plus M2 V2 initial in the x direction. And to find some of these, what you may end up having to do is to break your vectors. If this is V1 initial, here's V1 initial X, here's V1 initial Y. So you may have to use sines and cosines to figure out what those various things are. And at the same time, you'd have momentum being conserved in the Y direction as well. And so all that's going to happen in a two-dimensional collision, as opposed to a one-dimensional collision, is you'll end up with additional equations. You'll have one equation in the x direction and one equation in the y direction. And more than likely, in order to solve the problem, what you'll end up having to do is to solve these two things simultaneously, which may mean, you have to solve something in one equation and plug it into the other equation, or do something creative algebraically. But the basic concept is right here. So far, so good? Max, please shut up. So we also learned during chapter 8 that collisions come in two broad categories, right? The first broad category was what we call elastic collisions. And you should certainly know the difference between elastic collisions and inelastic collisions. Now, in an elastic collision, what's going to happen is momentum is conserved because momentum is always conserved. But in addition to that, you're going to have an additional piece of information. You're going to know that the energy, both before and after that collision, remains the same. Now, collisions tend to take place over a very limited space of, say, heights or whatever. So usually the potential energy wouldn't have time to change during a collision anyway. So mostly we're concerned about kinetic energy. So in an elastic collision, in addition to these two equations, I might be able to say that the kinetic energy before equals the kinetic energy final. And of course, I mean the kinetic energy of all the objects put together, so I should probably write that as a sum in each case. But that's going to give me a third equation, and sometimes that third equation will let me figure stuff out. Now, in the case of inelastic collisions, this statement will not be true. I'll have usually more energy before, and during the collision, some of the energy is going to go missing. It's going to get transformed into things like heat or deformation or sound or some other form of non-mechanical energy that we're not tracking. So it's not that the energy has disappeared from the universe, it's just turned into a form that isn't mechanical. And if that's the case, I'll end up with only two equations, I cannot count on this one being true, and I'll have to solve the problem with less information. You'll also note that there's a special kind of inelastic collision that we call the perfectly inelastic collision. And perfectly inelastic collisions occur when you lose the maximum possible amount of energy while still conserving momentum. Oftentimes, that means that the objects will stop completely, but not always. It does, however, mean that when you have two objects, a perfectly inelastic collision, you will see the two objects collide, and afterward, they will be stuck together, right? If they collide but bounce apart, it may or may not be inelastic. You're going to have to do the math to know which. But if they stick together, you know for sure it's perfectly inelastic. It could not be any more inelastic if you did any other combination of motions. That's the most inelastic it can be. So please, please, please don't make the mistake of assuming that just because two things don't stick together, that it's elastic. That is not true. They can bounce apart and it could go either way. But if they stick together, it is for sure this. All right. So those are the big concepts back in chapter 8. Learning how to deal with momentum and momentum conservation. Yeah. I guess I should probably say that there was one special equation that we did learn for 1D collisions that might be helpful. It's only true for 1D elastic collisions, but in those conditions and those conditions only, I can say that this is true. And of course, the companion to that I saw somebody pop up in the chat. What was the question? Yes. Stephen, was there context to that? Yes, because I'm not sure what to go with that. Oh, you were answering their question from earlier. Yeah, you answered that like 10, 20 minutes ago, dude. All right. So yeah, these two equations are true, but they are only true if I have a collision that is one-dimensional. And on top of being one-dimensional, I have to know up front that it's elastic, right? We got these equations by combining something like this and something like this. And we did some algebra, and it was long and annoying and crazy, but at the end of the day, it's simplified to this relationship, but it's only true if those two conditions are met. If you use this condition or this equation inappropriately, my response is usually to give you a giant red X and 0 points. So don't pull these out unless you really mean it. All right, but that's it. That's the kind of crash course in 10 minutes or less of what we learned back in chapter 8. So that's the big concept. The big concept in chapter 9 was the concept of torque. Torque is a twisting force. It's a force that makes an object want to rotate. And we defined torque as the product of two vectors, R and F. R is called the moment arm. R is the distance from the axis around which the object wants to rotate and the location where the force is being exerted. So if I'm opening a door by grabbing the doorknob and pulling on the doorknob, I'm exerting a force at the doorknob. R would be the distance from the hinges of the door to where the doorknob is. If I've got a seesaw that's pivoting around the center, R would be the distance from the pivot to wherever I grab and pull. So here, R will be this distance when I grab at this location. If I grab out here and pull, the moment arm is larger, and therefore I'm generating additional torque. Now, when you multiply these two vectors together, you would, of course, find the magnitude of the torque by taking the magnitude of R, which by definition is positive, times the magnitude of F, which again by definition is positive, times the sine of the angle between R and F. And of course, sometimes it is helpful because sometimes this angle is really annoying to find. Sometimes it is helpful to remember that the reason that we're doing this is because we're only wanting to find the part of F that is perpendicular to R. So oftentimes it's easier to break F into components that are parallel and perpendicular and only multiply by the part that is perpendicular. And sometimes that's easier than finding that sine of theta that we're talking about. But this only tells me the magnitude of the torque. It does not tell me the direction of the torque. In order to do that, you're going to have to remember the right-hand rule. Now, the right-hand rule says that you will take your right hand and you will put your fingers in the direction of whatever vector comes first. Notice I wrote R cross F, not F cross R, because if you flip the order, unlike regular multiplication, if you flip the order in a vector multiplication, you get different answers. So imagine I have R pointing up and F pointing sideways. I would start with my fingers pointing in the direction of R. Now I can have my fingers pointing in the direction of R, but I can have my hand oriented all kinds of different ways, right? However, what I want to do now is with my fingers bent towards R, I want to bend my fingers toward F. Now, the way I'm holding my hand right now, my fingers are toward R, but my fingers can't bend backwards, so I can't do that. So in order to do that, I'm going to have to rotate my hand. So I'm rotating my hand with the finger staying in the direction of R. And now, when I do that, I can bend my fingers in the direction of F. Once I've achieved that orientation, I stick my thumb out. In this case, my thumb is pointing downward away from the camera, which tells me that the torque vector is downward and away from the camera. So this would result in a torque away from the camera. So it is important that you guys be able to do the right-hand rule. There will certainly be questions about that. Please note you must use your right hand to get the right answer. If you're using your left hand, you'll get the wrong answer every single time. So put your pencils down if you're right-handed, do the thing, figure stuff out. Now, what does that direction represent? Well, in the case of torque, if you've got a torque vector, if you stick your thumb in the direction that torque vector is traveling, your fingers are going to curl in the direction the object wants to spin. So if I have an upward torque vector, that means that things want to rotate, if I'm looking at it from above, counterclockwise. If I have a downward torque vector, it wants to rotate clockwise as viewed from above. If I have a torque vector that points to my left, that's like something rolling end over end this way. So that's why we use one arrow to represent the torque, is because we have that convention about what that means. So in chapter 9, we have this concept of torque, and we only applied it to situations where objects were in static equilibrium. Now, when I say something's in static equilibrium, I usually mean that it's stationary. In order for it to be stationary, two things have to be true. The first thing is that there cannot be a net force on the object, because if the net force on the object were anything other than zero, then it would be accelerating, right? The sum of the forces equals ma. So if this is not zero, there better be some acceleration on the other side. But we can't have that if I'm stationary. So to be stationary, this must be true. It must also be true that all the torques have to add up to zero, because if they don't, the object would be rotating. And so in order to solve a static equilibrium problem, what I'm going to have to do is to treat it very much like a Newton's law problem. I've got some kind of object. Maybe I've got, here's a sign. The sign is being pulled by a string over here and a string over here and gravity over here. But what's going to happen is all these forces have to add up to 0. But in addition to that, all 3 of these torques have to add up to 0. Otherwise, the sign is going to rotate, right? We did a version of this same problem back in chapter 4 where we ignored the rotation part. We only did this part. But if I was to do this in the real world, I'd have to figure out how much torque around some kind of axis each of those forces was going to create. And that would be required. So that's the big concept, right? You identify your forces, do a free body diagram, but in addition to summing up all the forces, and in a problem like this, I'd have to split my forces into X and Y and X and Y. I'd have to do components for all of these. And then for my torques, I'd choose some place to be an axis. And the good news here is that I can put the axis anywhere I want. So if I was doing this problem, I'd probably put it right here. But then what's going to happen is, like, the torque from this guy would be this R times this F times the sine of this angle, is the angle between R and F. And then for this guy, it would be, that's my R, because it goes from the axis to where I'm pointing. That's my F. That's my theta. And I'd have to be able to figure out those things somehow. And I'd end up generating an additional equation from that. And then it's a matter of just solving what all those different equations are going to be. All right, so that was kind of a super rapid sort of run through the big concepts.
Wait, can you do the free body diagram again of that?
So let me redraw it so it's not so messy, right? So I had a sign, right? And I said there's a string pulling it here and a string pulling it here. So this string's going to pull it that way, that string's going to pull it that way. And of course there's gravity, and gravity actually should have drawn it here, actually. Gravity would be right there. So that's the free body diagram. And then when I was doing the torques, I was like, I got to pick some place to be my axis. I could put the axis anywhere I want. So I chose to put it at the location of one of the forces so that I got no torque from that force. But then the R is going to be the distance from that spot to wherever the other forces are acting. And I'd have to have enough information about the size and the shape of my sign to fill in all those blanks. So in terms of these 3 things, where do we feel like we need the most, I guess, review? If we're going to work an example problem, where should that example problem be from? Where do you feel least confident right now?
For me, it's torque.
Okay. Torque problems can be tricky. And let's not do this one. This one's kind of annoying. And I'd have to think through what information I'd give you to know how to make it work. Let's do one that's pretty easy. This is a problem that I had on an exam a few years back. So I've got a diver at a swimming pool, and they're going to stand on a diving board. And that diving board is supported by 2 supports. So these supports are sitting on the ground, and it's nailed in here, it's nailed in here, and they're going to stand on the end of the diving board and take a leap. And what I want to figure out is how much force is that going to put on the nails, or these 2 support stands, in order to keep that diving board stationary, right? Because if maybe these things can't support that much force, and this guy jumps on the end of the diving board, and one of these things breaks because I'm generating too much force on them. This could be a safety hazard. And if I'm an engineer who's building this thing, I certainly need to know what those limitations were. So let's specify some dimensions. Let's make this diving board be, golly, let's have it be 2 meters long. And let's have this guy nailed in at the very, very end of the diving board. And let's have this distance here be about, let's say, 1.5 feet, about 45 centimeters.
Does the weight of the person jumping on the diving board matter?
It absolutely will. Right? It's going to definitely matter. It's also going to matter how much they're jumping. All right. So far, so good. I'm going to specify that here in a minute. Now, we're going to have to specify some masses in this problem. And let's say that the diving board itself BOARD, thank you. So the mass of the diving board, let's have that be something like 10 kilograms. Now, the diver, let's put their mass at something closer to 60 kilograms. So I'll call the M1 and M2. So M1 is the board, M2 is the diver. And just to make things interesting, let's have the diver be jumping off. So let's say that he's jumping, and let's make it be straight up just for convenience sake, even though it's probably in the real world would be diagonal. Let's go straight up. It makes it easier. So let's say he's jumping straight up such that he's accelerating upward at, let's say, 2 meters per second squared. So that's what we've got. A 60-kilogram diver at the end of a 2-meter-long diving board with a mass of 10 kilograms. He is in the process of jumping upward with an acceleration of 2 meters per second squared. And what I want to do is figure out how much force I have to generate from those two stands in order for the diving board to stay stationary. Now, the way I'll start this problem is the same way I would any Newton's law problem. I'm going to generate a free body diagram and identify what forces I have in play. This is made a little bit more complicated by the fact that I have two objects of interest. I have the diving board itself, and I also have the diver. So I like to draw them separately so I don't confuse which forces are acting on which object. Let's do the diving board first. Now, on the diving board, I'm going to have a grand total of 4 forces, right? One of them is gravity, right? Gravity is going to pull on the diving board. It's going to pull that diving board down. And assuming the diving board is homogeneous, in other words, it's not super thick at the end and super thin at one end, I should assume that that force of gravity is going to act at the center of mass of the diving board, which is right here in the middle. So M1G is that force. Now, in addition to that, there's going to be forces from these two supports. And one force is going to be exerted at the very, very end. Now, is that force going to be in what direction will that force be? What direction is the force going to be from that board at the very, very end?
Can you repeat the question?
So there's going to be a force acting on the board from the support at the very, very end. And the question is, what direction is that force going to be?
Is it down?
Up?
You might think so. So we're going to go with that for now. Turns out it's going to be wrong, but we're going to do it intentionally wrong so that you can see how I would know that it was wrong.
Wait,
So
which one is wrong? Up or down?
up is definitely wrong. We're going to get this wrong. But I'm going to leave it like that because the first time I solved this problem, that's what I guessed also, right? It's not a stupid guess to make. It's going to be wrong. So we're going to treat it like a normal force. We're going to call that N1. And that's going to happen right here at the end of the diving board. Now, there's going to be another force from the other support. Let's assume that that one's also up. We're going to call that N2. By the way, N2 is definitely going to be upward. We got that one right. Now, are there any other forces on the board? Sure there are. Because what's going to happen is, if I go over here and think about that diver, let's do a free body diagram for the diver. The diver is being pulled downward by gravity. He's being pushed upward by a normal force from the diving board. But if the diving board is pushing him up with a force of N3, Newton's third law says he is pushing the diving board down with the exact same amount of force. All right, so this force and this force have to be the same because Newton's third law says if I push you, you push me equally hard, but in the opposite direction. So N3 is equally hard, but in the opposite direction. So far, so good? Okay. So once we have all this, what we're going to do next is we know that in order to be in static equilibrium, all of the forces have to add up to 0. So the sum of the forces must be 0. So if I'm looking at this diving board, I have 2 upward forces and 2 downward forces. I can write the following equation. I can say the upward forces, N1 plus N2 minus M1G minus, or sorry, N3 equals 0. So I just took the 2 up forces minus the 2 down forces. They all have to add up to 0 because if they didn't, the diving board would be moving up, down, or left or right.
Wait, so since that's wrong, then would the N1 and N2 be negative? That's what you're saying? Or
Well, what's going to happen is, yes. Like if I had guessed right, I would have said, aha, N1 is downward. I would have put a minus sign there. But what I'm going to show you is that even if you guess wrong, you're going to be able to spot it when you solve the problem. All right, so don't worry about it yet. Right? So I've got, if this were my free body diagram, that would be the correct equation. So far, so good? Now, there's no sideways forces, so all I have is this up and down F equals ma equation. But now I'm going to have to do another equation. And in that other equation, I'm going to have to do the sum of the torques. And in order for the sum of the torques to be 0, I'm going to have to choose an axis around which to sum them. And it doesn't matter where I put the axis because the object, if it had a non-zero torque around any axis I could pick, then it would be spinning around that axis. So anything I pick should still work. So I like to pick an axis that coincides with one of my unknown forces. And the things that I'm solving for are N1 and N2. So I'm just going to go ahead and stick my axis right here where N1 is. And when I do that, it means that N1 is not going to generate any torque at all because it's going to have a moment arm of 0. However, for each of the other forces, I have to use torque. And remember, torque is RF sine of theta. Now, all the R's are going to be sideways, and all the F's are up and down, which means all the angles are going to be 90, and the sine of 90 is conveniently 1. So it's going to be just R times F. Now, when I do N2, the torque from it makes this thing want to rotate counterclockwise. And I'm going to choose counterclockwise to be my positive direction. So N2 is going to be a positive torque. These other 2 guys are going to be negative torques because they want to make the diving board spin in opposite directions. So for N2, it'll be R, which is this distance here, 45 centimeters. So 0.45 meters times N2. This is the torque I get from N2. Then it's going to be minus, well, if this whole thing is L, this distance is half of L, so L over 2, times M1G, that's the torque due to the diving board's weight itself. Then it'll be minus again, because this is downward, it'll be the full length of 2 meters, so L times N3, and all of that's got to add up to 0. Super easy. So now what's going to happen is I want to solve this problem, and I'd like to figure out N1 and N2. Now, unfortunately for me, N1 and N2 both appear in the first equation, so I can't solve that yet. The second equation has N2, but not N1, but it also has N3. So I could get N2, but before I do that, I'm going to have to figure out what N3 is. So turns out I'm going to need one more equation to figure out N3. And that equation is going to come from this other free body diagram that I generated on the diver. Because if I do F equals MA on the diver, I can say that N3 minus M2G equals M2A. Notice the diver is not in static equilibrium. This dude is jumping. He's moving. But that means that when I go to solve for that, N3 is not just his weight. It's his weight plus some extra. The harder that guy jumps up, the harder he's pushing the diving board. So if he jumps up really, really high with a large acceleration, it's going to cause more strain on that diving board. But N3, now this, I can plug that back up over here. Let's go to a new sheet. So now I've got 0.45 N2 minus half of the length of the diving board times the weight of the diving board minus the total length of the diving board times the weight of the diver plus M2A. There we go. So all I did was I substituted and replaced from the previous expression, I replaced N3 with what N3 had to be, and it turned into that. So now what do I do? Well, at this point, everything in this equation is known to me because A was given to be 2 meters per second squared. The mass, this was mass 2, which was 60. That's mass 1, which is 10. L is 2 meters. So everything in this equation I can solve for. So let's just get N by itself. So I'm going to get 0.45 N2. I'm going to add all this garbage to the other side. Then I'm going to divide by 0.45. Now I'm going to plug my numbers in. Remember, I'm plugging in 2 where I see L. I'm plugging in 10 where I see M1 and 60 N2. So when I crunch all those numbers, I get a whopping 3,364 newtons. Sorry. When I do all of that math. So yay, I've solved for N2. N2 is finished. But I also wanted to know how much strain there was going to be on this guy over here. And what's going to happen is to solve for this, I'm going to go back to this equation because I haven't used this equation yet. So I'm going to plug in for this one because I now know N2, I know N3. I can solve for N1. So I'll have N1 is going to equal M1G plus N3 minus N2. And of course, remember N3 was plus M2G plus M2A. So M1 was 10, so it's 10 times 9.8 plus 60 times 9.8 plus 60 times 2 minus 3,364. And when I go to crunch those numbers, I end up getting negative 2,558. Now, here's the problem, right? I got a negative number for N1. And here's the issue with that, right? I assumed N1 was upward. But then I was solving for the magnitude of N1. By definition, magnitude should be positive. So the fact that I'm getting a negative answer tells me that something has gone wrong. I can't get a negative magnitude for a force because magnitudes are always positive. So what that tells me, the fact that we got a negative answer here when I solved for N1, is that my initial assumption about the direction of N1 was backwards, right? I thought that N1 is going to have to be upward, but in fact, what's going to happen is it's not that this thing has to rest on the stand, because when this guy sits on it, what this thing wants to do is to tilt like a teeter-totter. This part wants to lift up off the end. And if the nail weren't there, that's exactly what it would do. If you had this not nailed down and the dude stands over here, this thing's going to flip up and he's going to fall over. So in order for that diving board to remain intact, the nail on this thing is going to have to push downward to hold it in place. And how much is it going to have to push downward? Well, it'll be this much force, but it'll be downward. So had we guessed correctly when I did the free body diagram and drawn that arrow downward, I would have gotten the exact same answer. It just would have come out positive. The fact that I got a negative answer allows me to go back and rethink and realize that my original picture was not quite correct. So it's not the end of the world if you make a wrong guess. It's important that you be able to recognize what it means when you start getting negative values for the magnitude of forces. It just means that your original free body diagram had the directions flipped. All right, how we do? So, these sorts of problems are probably going to be the most algebraically problematic that you'll see on the exam. They'll require the most amount of work, but at the same time, they're also kind of sort of easy because the process is the same every time, right? Do the free body diagram, do equations for F equals ma and make A equals 0, do the equations for torque equals, well, you don't know yet, but the sum of the torques has to equal 0. You'll get some set of equations, probably either 2 or 3. And at that point, it turns into an algebra problem, right? But most of the points are going to come from doing the physics. The algebra it's nice, but it's not the important part of this class. So be able to do the free body diagram, generate your set of equations, and then from there, it's just a matter of manipulating them around until you get your answer. All right, we're out of time for today. So I hope you guys study hard. I'll see you on Monday.
Thank you.
You're welcome, guys.
Wait, I have a quick question.
Oh, yeah, what's up?
Well, like if I email you for like help or something, will you be able to?
You mean during the exam or between now and the exam?
Oh, no, between now and the exam.
Oh, yeah.
And
Yeah,
so how the exam
I have office hours, guys. I mean, that's so here, remember how this works. I have like standard office hours during my standard office hour times, which usually means that no matter what I'm doing, I'm sitting near my computer so that if emails come in, I will see them, right? If you set up an appointment, I'll usually set up a Zoom meeting. You can come in and we can talk through stuff and figure stuff out. No problem. Outside of my standard office hours, if you you set it up in advance. I'm usually still willing to meet with you guys. I'm pretty flexible because I realize this is hard. So yeah, by all means, set up a time. I'll come try to work through stuff with you.
Right. And how's the test gonna work again? I was late to class that one day.
So the exam's it's gonna go live sometime on Monday. It'll probably go live at the end of the day, like at 6 o'clock. And what's gonna happen is once it goes live, you'll have 48 hours to do the exam.
Oh wow.
Now, what will happen is the minute you open the exam for the first time, it's going to start a timer, right?
Mhm.
And I think it's probably going to be a 2-hour timer. So it's a time-limited exam, but you can start it whenever you want within that 48-hour period.
Oh, okay.
That makes sense?
So it's open for 2 hours.
Right.
but-
Yeah. Well, yeah. Once you begin it, don't try to. You can't start it and then walk away and come back later. You've got to do it in
Right.
2-hour settings. So set aside a 2-hour block during that 2-day period,
Mhm.
and during that 2 hours, you're going to be working on that exam. But you can start it whenever you want during that 2-day period
Right. Okay.
because your schedules are funky, right? And what'll happen is it'll look a lot like the homeworks in that it'll have questions and then blanks to put the answers in.
Mhm.
But the bulk of your score is not going to come from that final answer.
Gonna come from the work.
It's going to come from the work. And what will happen is there'll be 2 assignments. There'll be like the actual exam itself, and then attached to that, a second assignment where you'll upload, a readable scan of your work.
Right. Okay.
And after you finish your exam, I'm expecting that you upload the work pretty promptly. If there's more than about 5 or 10 minutes between when you finish the exam and when you finish the work, I'm going to start giving you the side eye, right?
Mhm.
But I'll be able to grade that for partial credit.
Right. Okay.
So that's how it'll work.
Okay. Thank you.
Yeah, you're welcome.